The next thing we're going to talk about in section 13.8 is the second partials test. Theorem 13.16 tells us that to find relative extrema, we need only to examine the values of f of x comma y at the critical points. However, as is true for functions of one variable, the critical points of a function of two variables do not always yield maxima or minima. Some critical points yield things called saddle points, which are neither relative maxima nor minima. As an example, if you look at the graph below, this would be the graph of the hyperbolic paraboloid f of x comma y equals y squared minus x squared. If we look at the point at 0, 0, so that would be this point right here on the surface. If you take any neighborhood in the plane x comma y, so here's 0, 0, take any disk around that point, you will find values of the function that are going to be greater than the value at 0, 0. You will also find values on the function that will be less than the value at 0, 0. So in this case, 0, 0 is not going to be a relative extrema. We give it the term a saddle point. Theorem 13.17 is what's called the second partials test. This will give us a way to classify our critical points as relative extrema or saddle points, or we'll look at a case where perhaps even this test might end up failing. Let f have continuous second partial derivatives on an open region containing a point a comma b, for which the partial with respect to x of f at ab is 0, and the partial with respect to y of f at ab is also 0. To test for the relative extrema of f, consider the quantity d, which is the second partial with respect to x of f evaluated at the point, times the second partial of f with respect to y, minus the mixed partial f of xy at the point squared. If d is greater than 0, and the second partial with respect to x is positive, then f has a relative minimum at a comma b. If d is greater than 0, and the second partial with respect to x of f is less than 0 at the point, then f will have a relative maximum at a comma b. If d is less than 0, and the partial of f with x comma of xx is greater than 0, then at the point we're going to get a saddle point at a comma b, and the test will be inconclusive if d is equal to 0. One of the comments that's made in terms of like where this test comes from, first of all, if d is greater than 0, the only way this quantity can be greater than 0 is you would require fx and fyy to have the same sign. For if these two had different signs, then this first term would be negative, the second term is always going to be negative, and that would produce a negative result. So anytime when d is greater than 0, these two will have the same sign. So in the test, it doesn't really matter how we state it. We could have worded this slightly differently. So when you see this condition here, fx, x, and fxx in the first expression, that could have easily have been replaced by fyy, the second partial with respect to y. One of the ways that might sometimes be helpful to remember this formula or expression for d is you can think of it as the following determinant. You can write d as the determinant of this expression. F xx, the second partial of f with respect to x, the mixed partial of f with respect to xy, fyx, and f double partial y. This would be equal to, if we calculate this determinant, this would give us our fxx, second partial of f with respect to y, minus f partial xy times f y partial x. However, notice that because we have continuity we're assuming continuity of the second partials. These two mixed derivatives would be the same, they'd be equal to each other, and so you could simply write this as the partial of f with respect to x and y squared. Let's look at an example using the second partials test. In example 3, they want us to find the relative extrema of the function negative x cubed plus 4xy minus 2y squared plus 1. We're first going to begin by finding our critical numbers, our critical points. So we want the partial derivatives. If we calculate the partial of f with respect to x, this should be equal to negative 3x squared plus 4y. The partial of f with respect to y would be equal to 4x minus 4y. To find our critical points, let's go ahead and see where the partial with respect to x and the partial with respect to y of f are both simultaneously 0. The first equation would give negative 3x squared plus 4y equal to 0. The second equation is going to be 4x minus 4y equals to 0. If we solve the second equation, we can move the y term over to the other side and divide by 4. We see that in order for the partial of f with respect to y to be equal to 0, that the x and y coordinate have to be equal to each other. We can use that information and substitute this into the first equation. Everywhere I see a y, if y has to be equal to x, then I can substitute that out for x, and we get this. Negative 3x squared plus 4x equals to 0. It's a polynomial equation. I can factor it, pull out the GCF of x, and then set each factor equal to 0. We get that x equals to 0. Over here, you would first subtract 4 and then divide by negative 3, and that would produce 4/3. The corresponding y values that goes with each x value, remember x is equal to y, so we're going to have the following values. X equals to 0, y equals to 0 will be one pair, that's the order pair 0, 0. And if x is 4/3, then y will also need to be 4/3. So we get 4/3, comma 4/3. These would be our critical points. We should also look for potentially where the partial derivatives would be undefined. So the second source of critical points would be either where fx or fy would be undefined. The expressions for both fx and fy are polynomials in the xy variables, so those will be defined everywhere. There won't be any other second source of critical points for this function. We now want to use our second partials test in order to classify these two critical points. Let me just write them above. We have 0, 0, and we have 4/3, 4/3. In order to complete the second partials test, we're going to need the second partial of f with respect to x. This is going to be equal to negative 6x. We also need the second partial of f with respect to y. This is going to be equal to negative 4. And we also need the mixed partial f of x, y. That would be just a matter of coming up here to the partial with respect to x and then taking that function's partial with respect to y. That should give us positive 4. Now that we have all of these, we can kind of go ahead and compute our d value. Let's take a look at the ordered pair 0, 0 first. D is going to be equal to fxx at 0, 0 times fyy, second partial with respect to y 0, 0, minus f partial x partial y of 0, 0 squared. If we stick 0, 0 into this partial, that's going to give us 0. The second partial of f with respect to y is this one right here. That's going to be a constant of negative 4 minus, if we stick 0, 0 into the mixed partial, that's going to give us the value 4. And so we end up getting negative 16, which is less than 0. If we go back to our second partials test, whenever d is less than 0, that means that that's going to produce a saddle point at that critical point. So 0, 0, if I were to plug this into the function, which I can do, let me just write it down here. Going back to the original function, f of 0, 0, if I plug 0 into this, that would produce the output of 1. So the ordered triple 0, 0, 1 is a saddle point for the function. Let's now go ahead and classify our other critical point. Let's see what happens at the ordered pair 4 thirds, 4 thirds. D is going to be equal to the second partial of f with respect to x, evaluated at 4 thirds, 4 thirds, times the second partial of f with respect to y, minus the mixed partial fxy, evaluated at 4 thirds, 4 thirds. If we stick 4 thirds into the second partial, that's going to be negative 6 times 4 thirds, which will be negative 8. If we stick the second partial into the 4 thirds into the second partial with respect to y, that's just going to produce negative 4 minus, and the mixed partial fxy is just the constant 4. This will produce 32 minus 16, which is going to be positive 16. So in this case, d is greater than 0. So d is greater than 0. And if you recall from one of our first parts of our calculation, the second partial with respect to x was equal to negative 8, which is less than 0. When d is greater than 0 and the second partial of f at the critical point is less than 0, we can conclude that f has a relative maximum at that location. So the ordered triple 4 thirds, 4 thirds, and I'll leave it up to you. I'm not going to show the computation on this, but you should go ahead and plug that x and y into the function to figure out the corresponding z value. but that order triple is going to be a relative maximum.